Well, I don't know why it doesn't like me. Oh shit, I don't like that. Any questions or issues? Oh, thank you.
Having surgery.
Okay.
So I also will be missing a day next week.
Yeah.
The laboratory, so I don't know if that's okay or if
So the lab, you can talk to the lab instructor. I
oh
don't.
no,
I don't
I'm
make
gonna have
rules. Okay.
laboratory.
Oh, you have lab.
Yeah, for like my body exam.
Oh, okay.
There's
Okay.
another way.
So does that mean the whole week?
No, it's just like for one day.
Okay.
So if I'm not here,
So we can record them all, so you can
Okay.
find them online. If you can't hear them or anything, let me know. You know, I'll walk you through the slides, but I post the slide basically in the next day. So if you don't see them in a couple of days, just remind me
Okay.
if I get up.
okay.
Okay.
Okay, thank you.
This is gonna be hard. I don't even know if that's possible. Nova, can you hear me? All right, something's gonna happen. We'll see how good it is. I'm trying to I went to this training today to see if we could make this room like that thing do this, but it doesn't give me an option. I don't know. I'll figure it out by Thursday, maybe. Okay. Good. Okay. Oh, so this Thursday, we will have another open house for the observatory. If you didn't come last Thursday, which I know is a lot of you, that's okay. You didn't miss anything. It's basically thousands of clouds. So we didn't see anything. But hopefully, I mean, it's crazy. There are clouds right now, and I like clouds. That's like what I do my research on. But they're Martian clouds, so these ones are beautiful. They're helpful for my job. In fact, they are hurtful for my job. Hopefully next Thursday we'll have clear skies and you can see some fun stuff. I think the moon will be at like 25% full, so we should be able to see like galaxies. That'll be fun. Any questions before we get started? Yeah. Maybe. Yeah, it's hard to project more than a couple days. Forecast says clear. So we'll see if that ends up being true. Yeah, it's perfect. Yeah. Probably the same time, so like between 7:30, 8. Okay. Let's get started. So this is the section of the class where I ask you to look at stuff and then you give me what you think you're seeing. I just realized now that this will be a little confusing because there is a little box on the top here. Let me just remove that. We're going to talk about planetary geology here. And just to get our brains working again. Come on now, let's do the thing. Oh my God. Okay. So what do you see here? Hands. Yeah. Where do you see a crater? This one?
Yeah.
Okay. Anything else? Yeah. Where do you see a volcano? Bottom right here or here? This one? Oh yeah, that's right. I don't know my right from my left. Honestly, I don't. Okay, so this one or where's the volcano? Oh, interesting. Okay. Yeah. This is a canyon? Okay, yeah, so maybe that looks like it's going down, okay? I didn't say this wasn't a volcano. I just wanted you to point to what part of the volcano. So this is indeed a volcano. Any other things you can see? Yeah. I don't have things to give away. I just got an Invisalign, but I don't think you want Invisalign trays. It won't fit your mouth. Oh yeah, so one, if you can't hear me, sorry. I'll try and enunciate. I have like now a lisp out of nowhere. It's pretty stupid. Anything else you see?
Like pointed stuff over there.
Yeah, so that's the pointed stuff and some like,
Is that
looks like
caves?
it goes down.
Is that caves,
Nope,
craters? I don't know.
this is maybe a crater, maybe it's a volcano. Can we tell the difference? Are we trained crater identifiers? No. You haven't even taught me this. What are you doing, Mateo? Okay, so what if I put them in color? Does it, I mean, can you tell what planets these are, by the way? You pick any one of them out, and they're not in color, obviously. The original ones might be. Any of them? Yeah. This one? You think it's Venus? Okay.
I want to see what left and bottom right. Mars.
Top left and bottom right.
Yeah.
Okay, so you think this is Mars and this is Mars?
I want to see that.
Okay, good. Did you have one? Bottom right is Mars. Okay, I got 2 votes for Mars on the bottom right. Ooh, you think that's the moon? Okay, a little controversy. What about this one? Yeah. That one's the Earth. Okay, that one might be a little easy because it's sort of seen from an angle. But maybe that's not correct. Stuff like that. Well, I haven't shown you that. I'm asking for people's opinions. Okay.
Top right.
Think top right? What about top right makes people think Earth other than the angle? Yeah.
Would it be for water? They're in, like in mountains, like rock.
Yeah, that's a very good point. Okay. All right. So let's see if we can do this here. Come on now. I'm gonna put them in color. Oh my God. Okay, there we go. So for folks who said top left was the moon, indeed that is the moon, and that is a true color image. Moon is boring. To the right, that's a true color image of Bryce Canyon. And that is formed by water, basically grinding down these rocks over millions of years. Bottom left is Venus. I forgot who said that, but yes, yeah, good eye. So these are fractures in the surface. Now we can't see the surface for reasons that we'll get into with our naked eye, but we can see it with radio waves. We'll talk about that later. And over here on the right, this is of course the best planet other than ours, which is Mars. This was a volcano, but it's also pockmarked with little craters, right? And so this is like a little lava flood that came down here. Okay. So we're going to talk about these 4 processes that I just sort of stated. We're going to break each one down. And these are the ways that the surface is shaped. We have volcanism. We already talked about that. Impact cratering. Those look really similar from above. We're going to see the slight differences. We're going to talk about tectonics. You may have heard about plate tectonics, particularly here in California, right? It's like the reason why hopefully property values will go down in the next 10 years. We'll have a big earthquake and everyone who's from out of state will leave, and then we'll have a bunch of nice houses to live in again. And at the bottom, erosion. You may have seen this yesterday. People's houses got eroded with water. Maybe their lawns got eroded, right? And we'll see this on geologic timescale. So on the top here, you have a volcano. spewing out stuff. A lot of people are familiar with volcanoes. Craters, you may not have an intuitive feeling for what a crater is, but I'll show you a lot of them. This here, if you go to Colorado or Boulder, you can see the process of tectonics. So this was sandstone, basically the bottom of the ocean floor, and it's been punched by rock that's coming up from underneath, and it's now exposed. So you have this beautiful red rock. And then on the bottom right, you have the Grand Canyon. Questions before we get started? Okay. Volcanism. What is volcanism? Volcanism is quite simple. It's eruption of molten rock onto the surface. Now I say it quite simply, but let's think about what it is. So we are all very much convinced that we are standing on solid ground, right? Anyone here grew up in LA? Okay. Did you ever think that if you kept digging under the dirt, you'd hit concrete? I did. I grew up thinking that there was basically concrete everywhere and you put dirt on top of it. Now the opposite is true. You put concrete on top of dirt. So what happens if you keep digging?
Like after the dirt or concrete?
Yeah, after the dirt and the concrete. Yeah,
There's more layers of rock underneath.
there's more layers of rock underneath, and eventually the rock becomes. What was that?
Red one.
Magma. Okay. So basically, magma is molten rock that's just under the surface of the planet. Okay. This is what we build a new material with. Another way of saying this is lava. So when magma makes it to the surface, it creates new land. Okay. There are three types. There's lava plains. These are flat, runny flows. There's shield volcanoes. We're going to break down each one of these. And there's stratovolcanoes. These ones go boom. These ones go, and these ones go. Okay, that's how you remember them. How viscous they are, how goopy they are. And while they do that, you know, we started with that picture a couple days ago of like a volcano, and it had all of this smoke coming out, and then like lightning in the smoke. That releases trapped gases. So underneath the surface, while there's lots of rock, there's also gas dissolved in the rock. So if you want more atmosphere, add some volcanoes that'll add gas to the atmosphere. Okay. Questions about this very simplistic idea before we get into the specific ideas? Okay. This is an example of a stratovolcano. You can see that it's outgassing there. So how does this exactly work? Hot in the middle. A fundamental concept we want to internalize. Hot goes up, cold goes down. Okay, you're sort of familiar with this. If you're boiling water, you put the hot at the bottom, hot goes up, cold goes down, gets heated, hot goes up, cold goes down, right? So here, the same thing is true. You may be very comfortable thinking that we're on solid ground. In fact, we're basically floating on a giant rock that's on top of a magma ocean. That's like being on a little ship, moving around, bumping into stuff. And sometimes the ship, you know, there's a little space between the ships and the magma comes out, creates new rock. And the reason that they move around is because of these cells. So here it's coming up, going to push it apart and make little volcanoes. And then over here, where it's interacting with everyone, it's going to push down and make volcanoes over here. Basically, anywhere that there is a fracture in the plate, you're going to have volcanoes. Right? Questions about this?
I do.
Yeah.
What causes all the heat from the, why from the?
Here?
Yeah.
Very good question.
Is it hot?
Very good question. So there, and we're going to get to this in some detail in a little bit. But yes, this is the hottest. And I'll tell you, I'll tell you why later. Okay. All right. Good question though. Okay, so there's three types of lava I promised you. We're mostly familiar with, say, runny lava from our nearest neighbor. It's called lunar maria. So these are the floody areas that make most of the flat surfaces. How did this happen? Well, when the interior, say, had these magma chambers that were quite hot still right after the formation, Sometimes you would just punch through it, just like gently punch it, and then it would sort of seep to the surface. It would melt everything around it. So if you look here in the bottom right-hand corner, you see the moon, and you have this like whiter material compared to this dark material. This dark material is all runny lava. So when you think about like obsidian or like you go to Hawaii and you get those like pieces of lava, that's the same type of material. Okay, that's why it's so dark.
You call it runny lava?
Runny, yeah, we'll call it lunar Maria for this. You can call it Maria, lava plains, call it runny, you can call it whatever you want. The exact name, yeah, go ahead.
Is there a way to like, is there a way to?
Good question. So is this currently still happening? Why do you think no?
Well, I think we would see like a lava, wouldn't we? Like it's all present and stuff.
Like red?
Yeah.
Yeah. So actually the moon is dead. Sorry, in case you didn't know that. And we'll talk about why the moon is dead and the earth is not. But this all happened a really long time ago. And in fact, there's something else in this image that tells us that it happened a long time ago. You don't have to guess it yet. We're going to get to that. But if you see it, you can say it. I just don't have anything to give you a prize. Okay. All right. So what happens when the lava is not runny? If it doesn't just seep, okay, then you get volcanoes. So you can look at something called the shield volcano. Shield volcano is pretty simple to understand. It's more like this than it is like this. Shield cone. Shield cone. So if it's like kind of runny, but not super runny, it kind of like builds up and then it'll just like move out really wide. And here, this is called Sapphis Mons on Venus. That's not a true color image, of course, because we can't see the surface, but I'll show you a different one in a few seconds. This one you might be familiar with. Maybe you went on vacation here. That's Hawaii. So Hawaii is a specific type of volcano. It's a shield volcano. The reason that Hawaii is a chain of islands, it's actually pretty cool. Oh, I should have drawn this. So there's a giant plate, and in the plate, think about a little hole. And that hole is leaking magma. And as the plate moves, it creates new islands. So here is the big island of Hawaii, and right here is a brand new island being created. So you can actually go and like take little tours, you sit on a boat, and there's like water and magma coming up. And you try to get close, like, woo! Or you can go up here, and this is still active as well. And people will like scoop it. Have you ever seen those videos? It's pretty cool. I don't know how you do it, but you take like a big stick and you like scoop magma and you put it into water to cool it off. And that tells you about the interior of the planet. So this is the Hawaiian seamont. If you look, they get smaller going backwards. That's because they're eroding with time. And in fact, this chain of mountains continues to go backwards, and it's mostly underwater. Okay. We have another example here on Olympus Mons. This is the largest volcano in the solar system, and it has friends. Arcia Mons, Pavonis Mons. I don't know how to say that last one. Mons just means mountain, but in a different language, I guess. Okay, and if we go back to Sapphis Mons, we can look at, you can see that it really is not just a mountain, but an active volcano on Venus. And we do that by looking at the thermal data. So we take a type of image that allows us to see where the hot is, and that's the hot part. So if I go back and forth, you see that this section here, is now overlaid on that topography data. Like where it's tall is also where it's hot. So we think there are probably active volcanoes on Venus, or at least that's what we're interpreting from this. Okay. Questions about this? So what are the relative sizes? This is sort of fun to think about. Where do you think the tallest volcano in the solar system? Any guesses? 1 in 3 chance.
Other Mars.
You go Mars. In fact, it is Mars. So here on the left-hand side, you see one of the smaller mountains. Maybe you have a friend who can climb Kilimanjaro, really impressive. It's almost 6 kilometers. Here's Everest at almost 9 kilometers, and Olympus Mons is 22 kilometers. This is so large that it's essentially sticking out of the atmosphere of Mars. This is so large that when you stand at the top of it and you look around, it looks flat. Let me show you why. Come on now. That's the size compared to Arizona. So if I'm standing here at the very edge of the caldera and I look off in the distance this way, it looks flat all the way to the edge of my horizon. And then it falls off dramatically. There is a little edge here. You stand here, I think it's like maybe a 100-meter fall. So don't do that. And what you can see about this surface, so this is probably where the major caldera was. That's like the inside of the volcano. The lava comes up. You can see that this was kind of runny lava because it didn't build up a really tall volcano. It built up a really wide one. So as material came out, it just kept flooding and moving out and then sort of getting cool enough to build up right at the edge here. Okay, this would have to happen for a really long time. And in fact, it did. So this entire region, when we talk about the geology of Mars, it was super active for a really long time. There's a plume of material that made this entire region warm, and you'll see that in a few seconds. Questions about shield volcanoes? Okay, so what happens if the lava is not very runny? And you get big booms, you get these ones. Okay, these ones are really fun. These are the ones that make these really beautiful pictures, these plumes. These are the ones that like shut down airports when they go off. There's so much material getting thrown out into the air. And you ever looked up the video of Mount St. Helens? Mount St. Helens was a stratovolcano. That's the type that has gases inside of the magma itself. And sometimes there's a lot of gases in that magma. And so if it can't get out very easily, if it's not just leaking out, then it builds up pressure. That pressure can lead to an explosion. Okay. So if you look up something like Mount St. Helens, you'll see there's a before and after picture, which I should have included. It's really cool. The normal mountain, and then after the explosion, it's just a hole. And you can see that that's in Oregon. Is that true? Oregon? Washington? Somewhere. Okay. Cool. Questions about outgassing as it relates to volcanism? Okay, so they're hand in hand. If you have volcanism, you have some form of outgassing. Okay. Let's talk about the second one. That's impact cratering. This one looks a lot like volcanism from above, but it's not. What is impact cratering? Yeah, that's exactly right. So you smack into the surface. So this doesn't have anything to do with the subsurface. Volcanism has to do with the place where magma is coming up from below and making a little, either a mountain, tall or short, or just running onto a plain. It's a fissure in the crust that magma can seep through. Impact cratering doesn't care. Just something coming in, smashing the surface. Okay. Usually asteroids or comets. And we'll talk about the relative difference when it's an asteroid or a comet.
What about meteor?
A meteor is a different word. So a meteor is, if you take something like an asteroid and you put it into the atmosphere, it becomes a meteor. If it touches the ground, it's a meteoroid. I don't know. We need words for things. Okay. Okay. So here's a question. You're going to participate in this. How many of the above objects, Moon, Mercury, Mars, Venus, and Earth, have impact features that can be identified today. Let me know with your fish. Okay, 3, 2, 1. Okay, interesting. Okay, I don't see anyone. Oh, I see one person with 1. A few people with 3, 4, and 5. Anyone want to defend their answer? Yeah.
I chose the moon, number 1, because if you look for telescope, like it's the one thing that has like very obvious, and very visible impacts, and multiple like all over as well.
Yes, absolutely correct. So moon is definitely 1. Is there any other?
Mercury, and Mars.
Okay, how do you know?
When you look at Mercury, you see impact craters, and then on Mars, there's also impact craters.
And on Thursday, I showed you a picture of Mercury and Mars, and I said they look really similar. Right, so yes, in fact, Mercury does have impact craters. We saw at the beginning of this class, there was a volcano in the bottom right-hand corner. There was also craters on it. So that gets us up to 3. Oh, interesting. Okay, so you think of here on Earth, there's craters?
Yeah.
All right, that would be 4. That's it, right? No. Venus does as well. Okay, so maybe a trick question, maybe not, but it's all 5. Okay. So most impacts actually happen right after the solar system was formed, in like a few billion years after everything sort of settled down. And we'll talk about this when we talk about the formation of the solar system as a whole. But one thing I want you to look at on the left-hand side here, this is a picture of the moon. And if you just stare at it for a little while, and people have done this, especially grad students, their whole job is to sit there and count. Okay, so up in the left-hand corner, you see this big one, the one big crater. And then that's sort of like a smaller crater. There's maybe 1, 2, 3 of those sizes, 4 of those sizes. And then if I look at this smaller size, 1, 2, 3, 4, 5, 6, 7. So every time that I make the size of the crater I'm looking for smaller, I get more of them. Right? There's lots of small craters compared to only a few big ones. Another thing that I notice about these, they're really circular. Some of them are like overlapping. So when people first looked at them, they thought that they were volcanoes. They're just like, the moon's super active, bro. I don't even know what to tell you. And they would have like these weird little mountains in the middle. Yeah.
Is there some of them look like they're not that deep, but they're more like surface level?
What do you mean by that?
Like the outline of it, but they don't look like they actually like really hit the moon.
Yeah, so this is really good, right? So some of these look like this, and some of them look like that, like a flat bottom, and some of them look like they have a bowl for a bottom, right? And usually the ones that look like they have a bowl for the bottom are the bigger ones, right? Okay, interesting. Why is that? These ones here, they're not as defined as some of these other ones. So that's also really weird. Some of them are more perfect circles. Do you see any that are like wide on the side, like an ellipse? The long one. The reason I think about this is, so people thought these were volcanoes, right? And some people said, well, what if it's like a rock or something hitting the moon? I said, no, you're crazy. That could never be the case. Because if I throw a stone at, say, sand, what shape do I get? I guess I should have brought sand, yeah. It's going to be irregular. So if you go outside, we could do this. But I don't think I should get in trouble for throwing a bunch of rocks. Grab some rocks, and just look at the dirt and then throw a rock at the dirt. Usually you're gonna get something that looks like a line in the direction that it was thrown. Maybe if you're lucky and it's like wet sand, you'll get like a big oval or a squashed ellipse. But unless you throw it right from above, you won't get a circle. So they were like, these can't possibly be impacts. Because they're too circular. And it turns out that people believed this up until the development of the nuclear weapon. So when we developed a nuclear weapon, suddenly we looked at where we had blown it up. We said, that's a pretty big hole. And they're like, it's a perfectly circular hole. And people just basically underestimated how much energy these objects, when they impact the surface, have. So I'm going to start you at the top and we're going to work down. So instead of just hitting like a rock that we throw at sand that sort of moves the top layer, impact craters burrow basically into the surface until they hit the hardest substrate that they can, and they detonate. They convert all of their energy, that was the energy from motion, into heat. And they melt to this area, and they spray what was inside out. Okay? And this leads to what's called an ejecta blanket. That just means stuff that left, that was ejected. And then you can see in the direction, all of this stuff comes backwards. And if you look along here, sometimes if you're careful, you can see the different layers that might be unearthed. So these are all layers that exist in the surface. Okay. And for comparison, come on now. Come on. So these produce a ton of heat. They can launch material up. Haven't even begun to talk to you about how large this object is, but see an object about that size creating a hole about 10 times. Okay. This has led to really poor financial decisions, not knowing this. Has anyone here been to Arizona? In Arizona, have you been to Meteor Crater here on Earth? Okay. This is Meteor Crater. It's also called Barringer Crater. Barringer is a funny person, or he was a funny person. So he saw this big old hole in the ground, and he said, that's an impact crater. And basically when this happened, millions of years ago, or 500,000 years ago, 50, wow, I'm really bad at reading today. They found like little pieces of iron nickel from the original explosion. And they thought the stuff that must have hit here is mostly iron and nickel. So if I just go right here in the middle and I just drill right down, I can pick up this huge piece of iron and nickel and I'll be rich. So he bought up all of this land and he created this whole mining operation. He just didn't understand what happens to the crater as it's being excavated, and what happens to the object that hit basically gets vaporized. So he wasted all of his money, but he got named a crater after him, which is kind of nice. And there's a nice little visitor center here. So if you're not familiar with this, it's about 1 kilometer. There's a visitor center here, and this is the road. I guess that's a bad joke. I don't know. Okay, so the joke is the difference between an astronomer and an astrologer. The astronomer looks at that and says, wow, look at all these different features you can see, like these rivers that are coming down into here and the layering, the sediment. And the astrologer says, man, it almost hit that road. Fine, whatever. Okay. And then this is me visiting it. So you can go there, it's really cool. This building, that building right here. So this is sort of the scale that we're looking at. You're looking down into the crater. I couldn't change the sun, sorry folks, but yeah, so you can see here, this is a relatively well-preserved crater. We don't have a lot of craters like this on Earth, mostly because the reason this is well-preserved is because it's in a desert. Yeah, so if I don't have a lot of water, say I don't have a lot of wind, you still see some impacts here, right? So you're seeing that this is sort of changing the surface as it sort of carves through. But the longer that we wait, the more this thing will just look like a hole in it and not like an impact crater. Now we won't get to see that because we won't live that long, but that's okay. So if I take this size scale, I'm now going to show you one on the moon. Okay, and yeah, okay. So this is 85 kilometers across. This one's really unique because there's a little hope in the middle. Okay, so this is this one here. You might have like looked up at the moon sometimes, and it's like white on the bottom. These rays that come away from it, that's the ejecta blanket of this specific crater. And you can see that it has sort of a, not just a crisp rim, it's kind of like broken up. That's because after the impact, lots of stuff happened. So first, why is it flat in the center? Well, it got really hot, it became magma. Why is it raised in the middle? Just like when you drop something into water and you get that little drip that comes back up, that's that little drip, but made of rock. So you punch into this thing, bam, melt this entire area. And this is responding, moving backwards and creating a central peak. And then this, mostly liquid lava, just sort of freezes around it and becomes rock again. This is large enough that the edge of the crater begins to fall apart. It's literally collapse. And so it doesn't maintain this beautiful circular structure. Okay. For scale, okay, we see 85, but that really doesn't make any sense to us. So there is the picture of, wait. Okay. Oh yeah, there's meteor crater. Oh, you couldn't see it before. There's meteor crater. Can you see it in here? That's this whole picture. Okay, that whole picture here fits there. Backwards. Okay, sorry, this thing, I hate this thing. I'm gonna get a new one, maybe. So again, this is sort of the perspective that we want to have here. These things are enormous, right? 85 kilometers across. And so if you're like a little human and you're walking, right, it's flat to you. you're barely seeing the edge over here. Okay. And now you can think to yourself, well, that's really impressive. It's a shame the Earth doesn't have anything as cool as that. And of course we do, because we're the best. This is in Canada. That's 100 kilometers across. Okay. This is actually quite old. 214 million years old. But because it's so large, it hasn't really eroded. Kind of hard to see. This is like the edge. Okay, you can see that there is water that's made it to the center. This is not the edge of the crater, this is water. Okay, and the edge of it is on the outside here. But it's very, very depressed. And for a majority of the types of objects that you'll see on the Earth, you have to use, I mean, this one's fine, you can kind of like see it with your eye. But for a lot of the other ones, you have to use other types of data, and I'll show you that in a few seconds. Okay. One thing that we want to draw our attention to, I pointed out, say like on the moon, that there are more large ones than small ones, right? And that actually tells us something really interesting. So we can actually use the fact that there are different amounts of different size objects to time stuff. So if there are a lot of small ones, say, then that would mean that they happen all the time. Okay? Lots of small ones happen all the time. One or two big ones happen infrequently. Does that idea make sense? Or have I lost me? Okay. So if I start over here on the left-hand side, let's say you go out with your friend, engage in adult beverages, and you're looking up at the sky and you see like a small shooting star, fire. Okay, that's this stuff. Happens on the hour scale, less than a meter. You in fact have to go back left a lot in order to see those. Over here, about once a year, once 100 years, you hear about like a new crater on Earth, right? Mostly they're just explosions. You may have seen like Chelyabinsk, and I'll show you a video of that if you weren't alive, God forbid. And then over here is when it gets like bad. So every couple million years, 100 million years and 1 million year. Sometimes you have like real tsunamis from impact cratering. And like over here, we're familiar with this one. Right, that's the dinosaur one. We'll talk about that in a few seconds. Okay. So has anyone ever been killed by a meteorite? Now remember that a meteorite is the stuff that's coming in before it lands. Yes, you think so? Probably.
But there was a couple years ago where a couple of them fell and some buildings in fact kind of got destroyed, like.
Yeah, that's Chelyabinsk. And I'll show a video of that in a few seconds. But did anyone get hit directly? Okay, interestingly enough, they haven't been killed, but Miss Hodges in Alabama in 1950 got hit with a piece of space. Pretty fucking cool. You're sitting there doing whatever you're doing. It comes through you. I mean, not for her, obviously, but that's pretty unique, right? Like, I don't know. She didn't die. There's a conference that I go to that's like asteroid, comets, and meteors. And in one of them, they literally had like this TV that someone was watching TV, and a meteorite came through the house, obviously broke through the window, and then through the TV. And so they just brought the TV to this conference so that people could see, like, here's the direction, we could see everything about it. So these fall all the time. And I could teach a whole class about meteors, but I'm not supposed to. So if you have questions, let me know. I'd love to answer your questions about it. Have they ever killed? Yeah. Yeah, it depends on their size. So we have tracked all of the big ones that are near us. So we can just look for rocks. In fact, there are people who spend their entire day looking for rocks that might kill us. And they look for small changes in their orbit, make sure that their orbit doesn't intersect the Earth. And the problem is that for stuff that is very big, easy to be seen, right? That's a simple idea. Very small stuff we don't have to worry about because it'll burn up before it enters. And there's a little space in between big and very small that we need to find all the objects. But as we mentioned, space is really big and they don't like to give us infinite money. So we can't do it very quickly. Okay. Okay, so has it killed dinosaurs? Yes. Not a real graphic, obviously these species weren't around for some time. But how do we know this? So essentially, we can look here at the Yucatan Peninsula for this Chicxulub crater. And can anyone here see the crater? It's a little harder because it's jungle, it's ocean. Yeah. Top left. You want to use the pointer? Push the center button. Yeah. Yeah, very good eye. Okay. You can also see this a lot better with gravity data. So this looks for like where is mass pushed together, and the force of this region on the spacecraft as it flies over is stronger. There's more material piled up there. So this entire crater, mostly underwater. I mean, half of it at least is underwater, and half of it is under a jungle. So it'd be really hard to see. It's kind of, you could kind of see it there in that picture. Okay, so this one was really important. We could talk about the death of the dinosaurs forever. So that's really fascinating. In this particular circumstance, this is not quite accurate, but this is kind of close. This is sort of what it looked like. You had a large object coming in, smashing into the Yucatan Peninsula. That was huge, by the way. Like I don't know if I included the size there, but this was so large that normally we see these ejecta blankets, small rocks coming out. This was launching rocks the size of Mount Everest. And it was sending them on basically trajectories like intercontinental ballistic missiles, so that they would not only just fall down right here, they would go all around the other side of the Earth and smash in there. So it would leave craters from this one impact all over the planet. When you think about, oh, how could one little rock kill the dinosaurs? Well, in fact, it did a lot of things. One, put a lot of dust in the air, vaporized the oceans near here, put all of that water vapor into the air, created shock waves, and every time that these would land, either in the water or anyone else, would create tsunamis. And then from this point here, you have this emanating ring of fire that would catch everything around it on fire. So for the sake of the dinosaurs, whatever they were doing at that time, they couldn't stand up for this. They were too large. They needed to eat too much. And in fact, what would happen is you would get basically it's like a nuclear winter. If you think about this, just like fog, not fog, smoke from all of the fallout here was basically blacking out the sky for many, many months, and whole biological ecosystems collapsed. Now, why did we survive, or our ancestors survive? We're small little cute mammals, and we would just like eat a little bit and then hide, and then eat a little bit and then hide. And dinosaurs went on to be chickens. Well, worked out super good for them. Questions about this part? I could do a whole class of dinosaurs. They're so cool. Keep in mind that T-Rexes, when you just like one little fact you can roll off, T-Rexes are closer to us than they were to Stegosaurus. We used to play with them as a kid. That was a lie. They never interacted. Okay. All right. So what do craters tell us about surface agents? That's this question. Come on. Okay. Compare numbers of lunar impact craters on the Maria, the Running Plains lava, to the highlands. Which of the two formed most recently? Is it A, the highlands, B, the Maria, C, we can't tell, or D, they're both the same age, 4.5 billion years old, and I'm going to show you the pictures right afterwards. The Maria is here, and the highlands are over here. And in case you're reading it, Maria, no, that's my mom's name. This is Maria. Okay. You want the original question, or you want this happen? Okay, let's have the question. Okay. Which surface formed more recently? The highlands, the Maria, we can't tell, or they're both the same age? Show me your fist. Okay, 3, 2, 1. Okay. All right, there's a good distribution here. Why don't you talk to your nearest neighbor, ideally someone who doesn't have the same number as you, and see if you can convince them of your answer. So you can turn around if you have to. You guys agree or disagree? Okay, so I hear the conversation dying down a little. Let's re-vote. Is it A, the highlands, B, the Maria, C, we can't tell, or D, they're both the same age? You can just show me when you have your answer. Okay. So less people have chosen 3 and 4. Does anyone want to defend either A or B?
Right, I said the Maria because, there's less, I don't know, from what I can tell, there's not as many big craters.
Mm-hmm.
And then it said they take longer to form, in the highlands, they seem like that.
Interesting. So you're saying the size of the crater matters, and that it's somehow related to time. There are less big ones in the Maria, so it must have formed earlier. Does anyone disagree with that idea? That's perfect. Okay, that's exactly what's happening. So less craters means younger surface. Okay, so an older surface has had more time to be impacted. So think about a car. Okay, you buy a brand new car. Does it have any dings in it? No. 10 years later, after you've been driving it and lent it to all your friends, and it's gotten hit by people, it's not your fault at all. It shows the wear of those 10 years. So older surfaces tend to have more craters. Okay? So it means that the surface has been paved. Does it mean that the planet itself is younger? No, because I can take it to a body shop and get the dings buffed out of it, right? So here we're thinking, okay, the surface is young, but it might not be a young planet, right? And we'll talk about how we can draw the distinction between those two. Okay. Okay, so we talked about the moon being dead. Really sorry about this. Hope no one was excited about this as a potentially geologically interesting area. The moon is very boring. We go there because it's close, not because it's fascinating. It's called geologically dead because geologic processes have virtually stopped. This includes erosion. So there is no atmosphere on the moon. So when you stomp on the moon like they did with this boot, that is going to stay there until you brush it. Nothing will happen to this dust unless it gets hit with an impact. Okay, there's no wind on the moon that's going to blow the dust away. There's no water that's going to like seep into the surface and move it. Okay, there's no tectonics that's going to shake it, no volcanism that's going to replace it. So the surface is dead. Okay. No. Come on. So I'm going to show you 2 pictures. This is a picture of Mars, and this is a map of Mars. That's Olympus Mons, massive. This is the Tharsis region, and these are really cool features. Like that's Hellas Planitia. This is the North Pole, the South Pole. We won't be graded on this, but I'm going to explain Mars to you. This is the largest canyon in the solar system, Valles Marineris. It's not formed by water running. We'll talk about that later. But this is the work of a graduate student at CU Boulder. Cannot imagine doing this. Must have been terrifyingly boring. So he went through and he found every single crater. And he recorded it as a dot. Okay, this is his graduate thesis. Dot. This isn't the highest resolution image, but you can find one of these. I can send it to you. And you can zoom in. He categorized every single crater. He would draw the circle on them by hand. I mean, that's like a specific amount of talent. So what do you notice about like this surface compared to this surface? If red is where the craters are. There's not as many, which means it's younger. Okay, so this surface near the volcanoes is younger than the stuff farther away. Does that make sense? Yeah, because volcanoes would melt the surface. Right? This lava flow would remove old craters. Okay, now here's a question. This is Venus. Stare at this for a little while. Venus doesn't have fun features that we can like identify and think about going to visit. Venus sucks. Mars cool, Venus bad. Just kidding. Okay, so which of these two is older? This one or that one? Yeah. This one has more craters. So this surface is older. Is that what you're saying?
Yeah.
Yes. Okay, so there's less craters here. There's certainly more craters here than, say, the Earth. Earth doesn't have a lot of craters, but the Earth has water. And when we talk about erosion, we'll see why that's so important. Venus doesn't have any water. And this is, I have time for this. Okay, the coolest thing about Venus is amazing. We haven't talked about tectonics yet, but the entire planet resurfaces about every 600 million years. What that means is that, we think about it as being rock and then magma underneath. Well, the whole thing just melts and then restarts. And that's why there are so few craters, despite being quite old. So there is absolutely no single part of the surface that's older than 600 million years old. And that is young. If you go to Australia, you can find rocks from 4.2 billion years ago. Pick them up. You can't pick them up, but people who are geologists can pick them up. Okay. Impact cratering is really cool. Tells you about the surface. So this is like our standard thinking of a crater. Punches into that substrate like we talked about, leaves a little hole. This one not so clear what's happening there. That's just because it's telling you about what's underneath. So this is 1 kilometer, this is 10 kilometers. This is ice. So after it gets heated, that ice becomes water, and that becomes like a muddy, essentially, and that makes it not so perfectly circular. Or here, maybe after a couple million years, wind or whatever will blow the edge of the crater and make it look really bad. Okay, this is all on Mars, by the way. There is wind on Mars. We'll talk about that in a few seconds. What is this? Don't say aliens. Yeah.
Is that the thing that happened in Russia with when it came down and
Okay. Very close. This happened in Russia, but not the thing that we were just talking about. Okay, this is called Tunguska. So someone walked over. This is in, I think, 1914. They're like, why are all the trees overground? The one that we were talking about earlier is Chelyabinsk, but they're the same event. So yeah, so this is Tunguska. Sorry, same type of event. Oh, okay. Well, I don't learn on TikTok. That's true. I do that too. Okay. So here, you see this circular shape. This is where all of these trees basically were burned to death. And crushed to death. I mean, they were alive, but not really. And so the reason for this is, so sometimes on the way in, you have this material coming in, has a lot of speed, but it's not dense enough or it's not large enough to make it to the surface to make that impact. So it'll burn up on the way in. And sometimes, especially if it's like, think about like a pumice stone you might use on your feet, or you might use to like sand something, that can break apart. As it breaks apart, it has more places to start burning from, and it can fully disintegrate. Okay, so for example, comets, when they come in, they're mostly like, they're very volatile rich. Those volatiles get hot and they explode. Okay, so we'll talk about Tunguska in a second. Let me show you Chelyabinsk. So this is that video. Who's talking about it? I forgot who was talking about it. But this is the cool thing. It's a dash cam footage from some Russians. They're just going to work. It's very neurotypically Russian. They won't even give a shit about what they just saw. Okay. Sorry, Okay, that's a factory. That is not. Okay, that is side. Factory, atmosphere, burning out, and a lot of light. Massive. Anybody thinking yourself, well, you're just going about their day. It's not that interesting. But what happens in about 30 to 40 seconds? Yeah, you'll feel the sound. But first you see the light, the speed of sound is much less than the speed of light. In about 30 to 40 seconds, depending on how close you are, you can feel the sound. It's not in here, but sorry, I got you really excited for that. There's other videos. So the problem is like everyone sees that, right? And they grab their phone and they run to the window. And this is, of course, what you shouldn't do, because you run to the window, you've gotten closer to the glass that's about to explode into your face. And so the people who got injured this way, right? You were talking about, okay.
Yeah.
I knew it was this section of the room. I just couldn't put it together. So yeah, so if you see something explode in the sky, please don't run into it. I don't know why. Here are the comparative sizes. So if you've gone on a flight recently, here's our Boeing 747. There's the Chelyabinsk meteorite, or meteor, I could say. That's Behringer crater. So that was iron and nickel. Notice the difference in material really matters, right? So this was iron and nickel. So when it did hit the surface, it made a real big mess. This is Chelyabinsk, more porous, wasn't that big a deal. It sort of broke up on its way in. This is Tunguska. That was the one that you were talking about, the Russian flat circle. So this stuff burst right over the ground, frying the trees underneath. Really big, but made of comet. So even though this one's really huge, it's mostly this like volatile rich material that as it gets hot, starts to burn very rapidly. So even though it's the largest of these three items, it doesn't hit the surface. Okay. Okay, that's all of impact crater. Okay, let's talk about tectonics. We're not going to get through all of these. That's fine. Tectonics. You have heard about plate tectonics. There are other type of tectonics. It's just the name for any sort of motion of the surface. Okay, so it's the disruption of a planet's surface by internal stress. And stresses is not like, oh, the homework's not coming up. It's like where you put a lot of pressure on something for a long time, right? So the way I like to think about this is like something like that. Notice I'm slowly moving. And every once in a while, I just fall, right? Those slips are earthquakes. The normal motion is the plates moving by one another, okay? Sorry that you can see that outline. It's a really cool demonstration. Okay. So here's tectonics. There's two flavors in general. You have compression and extension. And on Earth, we see this all over the place. Maybe I'll put this into the slides for next week, or sorry, Thursday. It requires convection to create these stresses. If you don't have any convection, then there is no reason that a plate is going to get pushed or that the surface is going to get pushed. Here, what you're looking at is the Appalachian Mountains in the US. These are getting pressed together because two pieces of the crust are crashing into one another. What's another place on Earth that two pieces of crust are crashing into one another? Creating the largest mountain on Earth. Yeah. It is Mount Everest. In fact, India has had it out for the sub-Asian continent for a long time. India started off far below, and Asia was up here, and India was like, and smashed into the bottom of Asia. That's why you have this entire Tibetan mountain range region from compression of the crust. On the right-hand side, you see these like linear things. This is the ground stretching. Okay, that seems kind of weird, but I promise it happens. It happens even on Earth. There is a place, you can't visit it, because it's under the water. So unless you're a Little Mermaid, you'll get there. It's called seafloor spreading. So at the bottom of the ocean, in between, if you've ever looked at a globe for a really, really long time, and we'll do this tomorrow, you've seen how like Africa fits up really well with South America, kind of put them together. Well, it turns out they're being pressed apart by this. So there is an upwelling branch that is pushing apart these plates and creating new magma in between that then cools and becomes crust. And every year, the plates get further apart. On the left-hand side of South America is left-hand. The western side of South America is anything we'll do here. Any answer?
The country?
Yeah, sure. Name a country. Chile? Chile's famous for
It's in
the Andes Mountains. Okay, why do the Andes Mountains form? Well, because of tectonics. Okay, here you have material that's crashing into one another. You have one plate that's going this way, and you have the Pacific plate going, or I think it's the Pacific plate, going like this. What happens is instead of squishing like they do in Appalachia, one goes down and one goes up. So where it goes down, there's actually quite a huge rift. And this is why the fisheries off of the coast of Chile are quite rich. Deep upwelling makes really yummy fish. Okay. These are tectonics. There's lots of examples. I could just point to a globe and we could go over it, but I think that I would lose you both today and in general. So this creates stresses in the crust. It requires a warm interior. If you don't have convection, you cannot have it. Okay. So does tectonics exist on the moon? No, because it doesn't have a warm interior. They can be global, like on the Earth. They can also be local, as we'll see in some other examples. And this idea of plate tectonics, even though it's like what we know and love, is probably just ours, or interestingly enough, the reason that we have water. So before we leave, let's answer this question. How can solid rock be bent, squished, cracked, stretched? Yeah. What's that? With heat, yeah. So that's definitely the case. The top of the surface that we're looking at right now is moving. So right now, you live in LA. That's great. In about 15 million years from now, your nearest neighbor will be San Francisco. Okay? You won't live to see that, hopefully. But that's not happening like because it's lava. It's happening because yeah, that's the name of what. Why is it? How can rocks change? Yes. This is maybe I'm not saying this right. This is on me. Okay. Rocks don't look like rocks over 15 million years. So rocks can change very slowly. And you won't notice it. So you're standing here on a day-to-day basis, you're not noticing that you're closer to San Francisco than you were 10 years ago. Why? Because it's only 10 inches, right? You haven't noticed a motion, okay? So the behavior of rocks depends on the time scale of the stress. If it's a long time scale, rocks can just flow, which is counterintuitive to think about. Rocks behave like silly putty, essentially. If it's short, then you get earthquakes. So if stress is released quickly, earthquake. If stress is released slowly, that's just geology. And I guess all geology, but you know what I'm saying. Okay. Depends on temperature. We already talked about this a little bit. If it's hot, it's easier to do. If it's cold, it's not easy to do. So at very high temperatures, rocks flow more easily, and at low temperatures, they're more brittle and they can break and snap. Okay, so if you think about, say, ice, for example, ice is more likely to just crack than it is to slide, right? Okay. Finally, let's talk about plate tectonics. Here is Earth. That's the subduction zone I was talking about before, creating the Andes, continental crust. We talk about all that. But on a place like Venus, you get blobs. Venus does not have plates. It's a one lid. And when it wants to create new crust, say from a volcano over here, the rest of the crust has to get out of the way. And it gets out of the way by literally squishing, like an accordion. So here's a picture. This is the picture we started with in the bottom left-hand corner. In the center, you'll see a volcano. And it's producing new material. You see all these rings around it, pushing the crust out of the way. So all of this fracturing of the, not Earth, crust is due to tectonic motion here. Okay. Questions, comments, concerns? Yeah. Very good question. This material is essentially basaltic, so it's very similar to the Earth. It doesn't have as much oxygen, and it's less wet. And it's less wet because, well, we're going to see later why it's less wet. The reason that it is a one lid, the reason why it's one plate, is because the crust itself is not hydrated. If you've ever thought about like using sand, moving sand between your hands when it's wet versus when, I don't know why you would do this, but if you've ever done it, if you move it between your hands and it's wet, it sort of slides easily. So plates that are hydrated can move more easily past one another. The absence of water makes them very brittle. And in fact, that's why the entire planet basically resurfaces every 600 million years. Something happened to Venus's water, and it lost its ability to recycle its crust. Okay, any questions about that? I think we're going to leave it there because that brings us to the fourth process, which is erosion. We'll talk about this on Thursday, and then we'll talk about what things force the differences in all the plants. Thank you. Yeah. Yeah. Really important. So I want to, I've done this lab before. Let's say you get a number, this group with the answers, how many things are you got? Yeah, let's say you did, you know.
No, but I think it's
Oh, yeah. What's that?
it'd be a mixture of big pieces and small.
Right. Every time you hit it, you get more. It's smaller. So in fact, this tells us a lot about how money is made. How they're made. Snap time and make them smaller. That's exactly right.
Because I noticed that one had a bunch of different operators.
Uh-huh.
And then the other one, that's just the graphic of it, but the other one did it, but I didn't.
Yeah, thank you.
I forgot. Like.
Yeah, no, that's a very good point. I'm glad you could see that on there. Let me stop the share. And oops, wait, where'd it go?